Okay, so last time we were talking about a space of conformal blocks, and we considered only 1 and 2 point cases. Although for 2 point case we can already get something non-trivial and infinite dimensional if we consider irregular representations of the Virasoro algebra. And now I want to tell about a 3-point case. Since it is since there are only 3 points, we can put them at 0, 1, and infinity. And we consider there are 3 places where we can insert some vector. So it is we say that there is this functional which depends on 3 vectors, like v0, v1, and v infinity, and this equals to the correlator of all of operator corresponding to this space, this state v0 of 0, all v1 of 1, all v infinity of infinity. So the first statement is that like, for example, let us say that we have some v0, then L minus K let it be just L L minus K acting on V1 and V infinity. So, the statement is that it can be expressed in terms of operators acting only on V0 and V infinity. So I'm asking the question, what is the dimension of this space? This can be realized at the following correlator. So in the following integral, integral around 1, z minus 1 to power k plus 1, and this O 0 O t of z O 1 O infinity. And since it is this is our epsilon, so we know that since integral the subject around all controls encircling this singular point is 0, we can transform this integral around 1 to sum of integrals around 0 and infinity. So it is uh, so the picture is this. So 1, 0, infinity equals to this. So it is minus integral around 0. Oh, basically it is no. Let us just try that. It is uh, no. So it is this one t of z of 0 or 1 or infinity. So it tells us basically that any three-point function with some descendants at the point 1 can be expressed in terms of this three-point functions with descendants at 0 and infinity. But it tells actually not only this. Because we can apply this formula for some special Virasoro generators. For example, let us see what happens when k equals to 0 and 2 minus 1. When k equals to 1 and to 0. So when k is 0, mm, mm, we see that this v0, l0, v1, v infinity equals to this integral around 0 is at z minus 1, and this OP is let us maybe write it already as a series of these linear forms. So it will give L minus integral around 0, L case, oh no, L some else, m's over z m plus 2, acting on v0, v1, v infinity. Minus integral around infinity was z minus 1 sum of minus n over z m plus 2. So this is one formula. So we will compute this integral immediately. And we can also write the same for k equals to 1. That's the same, but without this prefactor. Or maybe I shouldn't have written this formula. Maybe it's useless. I forgot actually. Sorry. Okay, now let us compute these integrals. Who? Where? Yes. So it was k plus 1. And oh no, sorry. Was it for? Oh, so no, it was for LKs. It was. And this is for LK because t of 0 of 1 1 is sum over K is O1 over C minus 1 to power K plus 2. So to get here it means K minus 1. So now it should be correct. Hmm? We assume that this integral is taken in the opposite direction. So the integral around infinity should be clockwise. Or what's the question? Yes. Mm, uh, No, it's a function. We have this function with an natural momentum tensor inserted, and we just take this function and integrate it in different domains. So, uh, and we know that OP of the natural momentum tensor with field at infinity is given by the same formula, but with opposite opposite label of the Virasoro generator. Or we can rewrite it like this: z minus m plus 2 is equivalent. Yes, it's a field of dimension 2, and transition function is z to 1 over z. So uh, this so if we try to change z to 1 over z, we should multiply by Jacobian, which is z plus or minus 4 Jacobian squared. So is it fine? Hmm? No, because we don't change this coordinate. We don't change z to 1 over z anywhere. We just expand the same function in different regions. So what we use is that like t of z o of like dz squared t of z o of z are equals to sum of dz squared over z to n plus 2 l n o of zr. And it can be equivalently. So if you take this OP and change coordinates, then we can say that d1 over z squared t of z o of 0 t of 1 over z will equal to sum of z squared over z to 2 minus n. I think so we should write so if z is 1 over w, t of 1 over w is w over w to 2 minus n.
Isn't that the left-hand side of above is equal to the left-hand side below?
So no, let me think. Actually, this is this acts on O of infinity. So I'm in between Earth. Last time it was something very trivial and clear, and wait. No, I'm doing something stupid. Yes, we uh, uh, so we say that we perform transformation z to 1 over z to 1 over z, and yes, energy momentum tensor uh, transforms to itself, because it's a definition of conformal invariance for the primary or quasi-primary fields. And the right-hand side of this expansion transforms in this way. So now we can cancel this squared in both sides and say that it is this expansion for z goes to infinity. So, and if you work on a cylinder, then this extra terms like n plus 2 can be hidden in this squared, because it is a really d log of z squared. So in cylinder coordinates, it will become just a differential of that cylinder coordinate. Is it fine? No.
Like the coordinates z, okay, because you have z around infinity, right? So in principle,
Yeah.
I should work in the patch around the point at infinity in the projective plane. So I mean, I don't see why shouldn't I transform also the no, because I'm imagining like the point at infinity is like I take a point at a finite point in my projective space and I take the limit at infinity.
Yes.
Okay. So what I need, like when I do something like this, I get like the transformation rules of O are even when you say O to infinity, basically. Like when I do the procedure, the transformation rules of O infinity already means that you have z to the delta or z limits infinity.
Like R to delta. Yes. R to infinity.
But like if I do something like this, why shouldn't I transform also the because now my coordinates like if I go at like if my coordinates this now is around zero basically, no? In the new coordinates.
Oh, so this point 0 after the transformation turns into z equals infinity. So.
I mean, or can also interpret like I have the point at infinity in my new coordinate is zero.
Oh, yeah, so we can say that it is.
Like z is a number which is very close to what? To zero or to infinity?
Yeah, here it's close to 0, here it's close to infinity.
But yeah.
Oh, right. So it's fine. Ah. Ah. Okay, so now we need to integrate these integrals. They're quite simple. So on this one tells us that V0, L0, V1, V infinity is what? This term will give L0 minus L0 minus L0 v0, v1, v infinity. This term will give L minus 1 acting on v0. Is it? So now this integral is in opposite directions, so it will come with plus, and so this first term will give L0, V0, V1, 0, V infinity. And this term with 1 will give what? It will be n equals to 1, I think. Let me think. So the second integral gives V0 L minus 1 V1 infinity is so this one gives L minus 1 0 V1 V infinity. And here M will be so it will be minus 1 plus oh, So now I want to do the following. So in principle, we would like to remove this L minus 1 acting on we want to know what is the value of uh, wait, how to say this mm, sorry. Let me first tell why I'm doing all this. So what is our problem? So we checked here that in principle we can remove any Virasoro generators acting on the first field and move it to 0 and to infinity. So in principle we can try to reduce everything to this problem, but then we still need to compute matrix elements for such states at 0 and at infinity. And the problem is the following. We have some LKs, LK, which is maybe well, so mm, if we want to move L minus K acting on V0 to infinity, acting on V0, so V1, V infinity, so it is given by the integral around 0 z to what? To minus to 1 minus k. At 1 minus k. Correlator of t of z. V0 O 0 O 1 O infinity. So d0 over pi I. So when we move this contour, we have one term where it is V0 with 1 LK V infinity. And there is another term which comes from a residue around 1. So minus integral of dz over or dz over 2 pi I z to 1 minus k. And here is 1 over z minus 1 squared. To 0 with 1. Mm. We see that computation of this integral gives this normal term, but we get again this L minus 1 acting on V1. And we should do something with this. And there is this term which is proportional to 1 minus k V0, L0 V1, V infinity, and plus also plus k minus 1 and minus this term with V0, L minus 1, V1, V infinity. So it appears again, and we need to show that this term can actually be expressed in terms of in terms of expressions with with L's acting only on V0 and V infinity, and that we don't increase the order of these vectors. So, namely, let us look at this expression and take some of them, because so the problem is, are these L minus ones which appear somewhere. So for example, it is here, and it is here. So we can write the following relation: that V0, L minus 1, V1, V infinity equals to equals to what? So these terms also cancel. So yeah, it is fine. Equals to minus V0, L0 V1, V infinity. this term, then these cancel, minus O0, V0, 1, V infinity, plus 0, V1, O0, V infinity. Yeah, so we obtain this relation that insertion of L minus 1 in the intermediate point it can be expressed in terms of L0, and L0 acts diagonally on the Verma module, so we can compute this. And so this this term in this expression, so both of these terms in this expression are well defined. And so remember, it's actually the same computation as we did when we wanted to compute matrix elements of the vertex operator between arbitrary states. But in that case, we had to say that L minus 1 is the derivative, and we know the dependence of the correlator. But very similar formula can be obtained just from the definition of conformal blocks. Like at this moment, nothing depends on z. So point 1 is just a fixed point. So if you want to replace z by 1, we can say that so it is a kind of correlator at it is a kind of a correlator with points at 0, 1, and infinity. And if you want to make it z-dependent, like v0, v1, v infinity, we can say that it is z to minus L0 acting on minus, or maybe minus L0 V0 z to minus L no that's fine. So if you define it this way, then we see that the cell minus 1 starts acting as the derivative. So and So, are there any questions about this? So if we have such kind of relation, then we can uh, pull all these operators from 0 to infinity and back, and reduce everything to the computation of computations in the Virasoro algebra. But now I wanted to show some example where, well, and the consequence of all this is that dimension of the space is 1. Mm. So, because everything reduces to a 3-point function of the highest vectors. Mm. So, but now I wanted to show an example where this space of 3-point conformal blocks is more than one-dimensional, like actually infinite dimensional. So let me check according works. Double-3 algebra. So it's an algebra which contains an momentum tensor with its OP, like mm, like yeah, like this. No, squared. It also contains a field of dimension 3. And OP of this W of W with itself. It is actually I already forgot the formula for it. So it's something like C over 3 or over 6. I forgot precisely. So I'll tell you about this more some other time. So here I forgot what coefficient. So it's the only field of dimension 2 which can appear here. And there is also some field of dimension 4, like lambda of z plus lambda of w. Maybe it's better to write it in the intermediate point. I don't know. And this lambda is with some coefficients t squared, normally ordered, plus second derivative of t. So there is such such algebra. So and primary fields of this algebra are defined by similar relations as for Virasoro algebra. So there are Virasoro primaries. T of z of w is delta actually maybe it's a mistake to use w as a point, z minus x. No, maybe it's too complicated to change everything. But let us use x. The of x is delta over z minus x squared plus oh, I can write here L minus 1 acting on O of x, L minus 1 O of x over z minus x. And this generator of spin 3. So the logic is the following. So if it is something of dimension 2, then a primary field is something which is scaled by all positive modes of this generator, and is eigenvector of zero mode, and some number of small negative modes acts somehow. So in this case, this OP should start as some so-called W charge of x z minus x cube plus some generator W minus 2, W minus 1 acting on O of x over z minus x squared plus W minus 2 O of x over z minus x. And it's actually a problem, as we will see now, because in the case of Virasoro algebra, although we had some generator acting on this operator O, we were able to express its action in terms of action on the other vectors. And but here it will be more complicated. So maybe I prefer to use this formalism of Brand cat vectors. So basically what we need to compute now is such matrix element, delta infinity, W infinity, some number of negative generators of Virasoro, some number of negative of positive here, y prime, W y prime. Maybe, well, it's actually, let us actually restrict ourselves to the 4-point conformal blocks so that we have non-trivial generators only on one side. it is O of 1, and here we have some W minus Y, W of minus Y prime, acting on delta 0, W0. Well, the question is how to compute such object, and what remains at the end. So hmm?
Okay, let me put context here. So what is like what is W? Like what should I think about W?
It is so it's a kind of a extension of the Virasoro algebra. So like originally, no, maybe free boson is not a good example. For example, if C equals one, uh, no. So, like, how to think about this W algebra? Uh, oh, let me maybe write a definition. Oh no, I don't remember the formula for the central charge. Mm. Let me write the formula for C equals to 2 for simplicity. And let us take two free bosons, but better to say that it's not two, but three free bosons, phi 1, phi 2, and phi 3, such that phi 1, phi I of z, phi j of w is minus delta I j minus 1 third logarithm mm, of z minus w. And then T of z is minus 1/2 sum of oh, so 1/2 sum of t phi I d phi I normally ordered squared I equals to 1 to 3, and W of z is I don't remember the coefficient, but it is sum over I less than j less than uh, mm, oh, maybe in this case it's just a product of three. Yes. Is it okay? normally ordered. So it can turn out that symmetry algebra of our theory is bigger than Virasoro algebra. So and there can be some other kind of integrals of motion, and so in this case of free fields, so if we take if we take one free field phi, and then we can generate, we can construct Virasoro algebra, and like a character corresponding to this free boson is 1 over 1 minus q qk, and the same as Virasoro character. So boson the same as Virasoro character. So if you fix zero charge if you fix zero more charge for this phi, then this is that this free bosonic module has almost the same size as the Virasoro module. But if we have two independent fields, sorry, I forgot to write here that phi 1 plus phi 2 plus phi 3 is 0. So and it can be seen from here. So, but so if you have so effectively there are only two fields. So if you have two bosons, then we have a character of two bosonic Fock modules multiplied. And if we try to represent it as a sum of Virasoro Verma modules, there will be infinitely many of them, because character of Verma module is just this one, not squared. But if you have if you construct another generators which are cubic in bosons, then characters of this W3 algebra, character of this W3 algebra becomes the same as this character of two bosons. So there is a high chance that Hilbert space of these two bosons is a single Verma module of the W algebra.
Okay, so you're saying that if I understood the reason, so if I have just two bosons, basically the interspace is just the tensor product of the two interspaces, and the character is just basically the product of the two characters.
Yes.
Okay, and this we can never achieve as a single module.
Of course, there will be infinitely many Verma modules.
Which corresponds to
to something. Let me think. Oh, it's not obvious because Virasoro generators do not commute when this W algebra generators. So we should. So from this point of view, we should take all this W algebra states and find Virasoro highest vectors in each so on each stage of this big drama module. But it is clear from the character because this is Virasoro character 1 over. This is chi Virasoro times 1 plus q plus q squared plus 2 q cubed plus and so on. So it means that any representation of the Virasoro algebra is well, if we are in in general position, it's a direct sum of Virasoro Verma modules. And if you want to count how many of Verma modules with given dimensions is there, it's enough just to compute on this character. And we see that there is infinitely many of them. So is it clear? I'm saying something absolutely trivial. I'm just saying that it might happen that some theory has not only Virasoro symmetry, but also some higher spin symmetry, which combines infinite number of modules to a single W algebra module. And it is a kind of analogous to this jump from, for example, group of global conformal transformations generated by three vector fields to entire Virasoro algebra. So if originally we had some infinite number of modules of this SO2, after this combination, it turns out that the Hilbert space is divided into much bigger pieces, and any quantities which involve some descendants of primary fields can be expressed in terms of quantities related to those primary fields only. So I don't know. Yeah, answer somehow or not. So, and there are some other cases where the symmetry algebra is bigger than just Virasoro. It's one of such examples. So when there are some other generators, yeah. So basically, if you if you now want to compute 4-point, so why are we computing this object? This is because if you want to compute 4-point conformal block, like delta infinity, W infinity, all of 1, all of t, all of 1, delta 0 w 0. Then we can insert this this resolution of identity. So it is L minus Y, W minus Y prime, some inverse Shapiro form of what of Y Y Y Y prime Y tilde Y tilde prime. W Y prime tilde O Y tilde O T of T, and this 0 delta 0 W 0. So it's again a gluing of this 4-point sphere from two three-point sphere. And this 2-point conformal block, or I don't know if it is correct to call it this way, but anyway, this object which yeah, maybe it's kind of a 2-point conformal block. This correlator of two descendants just gives Shapiro form as before, because it used a very simple argument that if some generator had positive index in one point, then moving to the other point makes its index negative, and then it kills everything. Or we can just think this way, that if you have some OK, WM, and here the operators with negative indices L, W minus P, then we can swap them using algebra relations, and all of them will kill corresponding vector. So this depends only on the commutation relations of this algebra. But if you want to compute such correlators, it is more tricky. Because now we will have the same problem, that when we move the generators through the primary field, we will get descendants of this primary field. So, namely, let us compute the commutators of L's and this primary field. Maybe it's I don't know which correlator is easier to compute. Well, so you may remember that. So this commutator with of OK with O is what? It's delta K plus 1 O. Let us actually rederive on this. Maybe let us start from from W. So we have this OP, W with O, and we want to compute the commutator of WK with O. So it is this integral over O of 1. It is this integral. So in one case, so it is 1, and in one case, absolute value of z should be bigger. In the other case, it is smaller. So it is dz to z k plus 2, integral around 1, the counterclockwise direction, w of z, O of 1 over, yeah, that's all. So it is integral around 1. Maybe let us put some point t. But I'll do this. Okay, so now compute residues, and we get k plus 2, k plus 1 times what times t to 2k w o plus k plus 2 t to k plus 1 w minus 1 o plus w minus 2 o. And if we do the same with the Virasoro commutator, then okay with O of t will equal to k plus 1 t to the k delta O plus t to the k plus 1 L minus 1 O minus 1 O. Right? So in principle, we can we might use this commutator, but it is not nice because this commutators produce this a higher a higher order terms. No, what I'm saying, these operators, when we commute them with primary field, produce this, this, and this. So the idea is that we can change basis in this W algebra in such a way that most of these operators commute with O. So because we see that a number of linearly independent terms here is quite small. So here it is 3, here it's just 2. So so for example, as a warm-up example, we can try to derive the statement about conformal blocks on a three-puncture sphere to understand that their space is one-dimensional, that everything can be expressed. So we would like to get rid of this term, L minus 1 acting on O. And to do this, let us consider the following operators. So operators are L, so T minus K, L. So first let us decide what we want to compute. Let us say that we are computing such correlator, delta infinity, LK1 and so on, LKN of T delta 0 in this one. So let us take operators L there should be some name for them, probably. Let's call them Vn. No, V is bad. Oh, An. And let us define them like T minus K L Lk minus T minus K minus 1 minus K plus 1 L K minus 1. So advantage of this definition is the following. That, let us compute a commutator of n with O of t. And it is what? So this term is uh, this term is uh, k minus 1, so it is just delta O. And this term, second one with O minus 1, just cancels. So it is easy to pull such operators through our primary field. And the last thing to notice is that there is an operator. So which one? One moment. Ah, so and of course, it's enough for us because so there are these operators and there is also operator L0, which we know how it acts. So if you want to express our Virasoro generators in terms of this, then L one is L0 plus um, plus um, maybe better to write this t minus 1. L1 is L0 plus A1, t minus 2. L2 is L0 plus A1 plus A2, and so on, right? So we can express such correlators as some combination of the operators where here we have delta infinity, here we have some L0 to some power A1, A2, and so on, O of t, and delta 0. Well, this L0 acts by some number, it's not a problem. And this A's commutes with O given the dimension of O. And all these A's act on delta 0 either by 0 or by again by L0. So so in this way we get that it is some number. So is it clear? So this term never appears.
So in 1 p.m. they are all positive integers.
Yes.
Okay. Now you're saying that when we act by AK on delta naught or delta infinity.
So when we act on delta infinity, it is something. Yes, any descendant can be represented in such a way, as a linear combination of something created by these A generators. Because we see that positive Virasoro generators can be expressed in terms of this A's. This A is just a discrete derivative of the Virasoro generator and its index.
Okay, but I mean, I don't see I mean, it's a correlation function, right? So it should be a number in any case, no? I mean, this should be a number independent from the representation in terms of A, no?
No. When I write here a number, I mean that this is a number which can be computed only from the computation relations of the Virasoro algebra, or from such algebraic relations.
Okay, now I see the point. Your point is like that on O, N doesn't act diagonally, but creates also other operators from O. But if I act with A, then this is just a number, and this is just basically an action of
So if you pull this A's to delta zero, then all of them except this first one will act by zero, and the first one will act by minus L0. Yeah. So the statement. Well, actually, we derived what we already knew. But now go to this example. And here we see that it contains some constant term. Oh, sorry, here I forgot t to k plus 2. So here we start from so here we need to take a second discrete derivative. Namely, we define operators Bn, which equal to
Sorry, I have another doubt about this expression. So when you say I mean, in the end, that expressions you're able to reduce to the expectation values of both t, basically.
Yes.
That's basically what you're saying this is a number.
Yes.
The reduction is just done through the commutation relation, and then I'm just left to compute the expectation values of both.
And it is, well, we can put here all of one. It does not matter, actually. I could put it from the very beginning. And it will be just some number, 3-point function. because those three states are primary states. So three-point function of primary states in general situation is something. It's additional information about theory.
Okay, but if you, I mean, if I didn't construct the A case, like what would have been the problem? That in principle I generate other stuff like n minus one of those or something like this.
It was somewhere on that blackboard. So if you try to move LKs from one state to another one, we get L minus 1 acting on the intermediate state. And the question is whether it can be expressed in terms of something else, or we are left with this object.
Okay, and we refer positively already at the beginning of the lecture
Yes.
by those identities, and now we want to do the same with this extended algebra.
Yes. Yes.
Okay, but like in this case, we have not yet used the double part of the algebra.
Yes.
This is just simple Virasoro.
Yes, so this worked only for the Virasoro part.
Okay, but this is basically another way to do what we already did in the beginning of the lecture.
Yes, of course.
Okay.
And so just another way to see the same, actually in a little bit different situation where we have only one non-primary state. But let us move to this situation. So let us do basically the same first. So we define bk to get rid of this w minus 2. And this bk is t to minus k wk wk minus so here we want to compute on this matrix element w infinity l k well, l some else and then wk1 wkn o delta 0 w0. So here it is t minus k plus 1 l w k minus 1. So computation relation of this operator with O is what? So O is for the first part it is this um, k plus 2 k plus 1 minus k plus 1 k minus 1 it is maybe 3 w all of yes 3w no 3w k plus 1 o plus t w minus 1 O. That's all. And the question is how many such operators do we have? So we have B1, which is double T minus 1 W1 plus W0. Have B2, which is T minus 2 W2, so minus W0 minus W1, and so on, right? Mm. So we are still unhappy because this term we don't know what is this term. So we need to take another derivative in k, which is ck is bk minus bk minus 1, and then a commutator of ck with O is 3WO, well, just this, nothing else. And if you want to express this case in terms of b's, so the first b which we have is b1, and here, so the first c that we have is c2, because we don't have b0, so we have c2 equals to b2 minus b1, c3 equals to b3 minus b2. So if we want to express all W generators, we need to take all these C generators and the first one of this, B1. So if you want to express expressions for the W generators are the following. W1, better to say like this, that we can express any generator in terms of these C generators and W0 and W1. So let me write this. So there is W1. Then W2 equals to T minus 2 W2 equals to C2 plus B1, which can be expressed in terms of, which can be written explicitly. T inverse W1 minus W0. T minus 3 W3 equals to C3 plus C2 plus T inverse W1 minus W0, and so on. So this is the problem, and this this set of generators which we get in this case is W1, C2, C3, and so on. So if we try to compute some matrix element, then this C's can be pulled through the primary field, and we are left with the infinite number of objects of this kind, delta infinity, W infinity, W1 to power k, O of t, delta 0, W0, not fixed, a kind of independent. So here is so in this case, dimension of the space of conformal blocks is infinite. When those are conformal blocks of the W algebra, even in between the primary states. And but sometimes there are some happy coincidences. For example, if we consider such a representation of W algebra where W minus 1 where this action of W1 is actually proportional to the action of L1. In this case, of course, we see that these matrix elements are computable, and and in this case, space of conformal blocks is of course is again one-dimensional, but in the general case, it is infinite dimensional.
But W1, how does it act on the states W's?
It's which?
Like, because the state W's are the primaries of the W part of the algebra, no?
Yes. So in a kind of in the same as to act by L1 in some sense, because in the sense that it is just some descendant in this W algebra module.
Yes,
so,
indeed, but wasn't it the same as above, in which we had descendants of in the Virasoro algebra?
no, what do you mean?
In the example, like the one of L and X.
Which?
Like just like the one that you brought in another.
Okay.
Like that. Yes, there. There we have K1 and Kn acting on delta infinity, no?
Yes.
And this is in principle is the same as W1 acting on W infinity, no?
No, there are, so we have both L generators and W generators. We have, yeah.
But I mean the the W states they form a Verma module of the W generators, no?
Of W algebra. So states are of this kind. We act with L's and then with W's.
Yes, but
Yeah.
okay. So I can form sectors with definite eigenvalues of W naught.
No, because W naught does not. So it is true that L0. No, of course you can find. You can diagonalize W naught on each stage, but it is not true that its eigenstates will be nice, because its commutation relations, for example, with W generators are what? So Ln with W m is I think 2 n minus m Wn plus m. Let me check this again. So if it like this. So if you take W naught, then no, maybe for L generators it is. No, even for L generators it is not right because Ln with W naught is 2n Wn. So you see that if you try to diagonalize, if you try to diagonalize the action of W naught, it will be something non-trivial. And for example, if you compute Wn with W naught, it will be what? So we have an energy momentum tensor in the correlator, so it will be some n maybe cubed, yeah, something like n cubed ln plus n lambda n up to something.
Okay, but then, sorry, so how is the model structure of these W algebras?
There is O0 which counts the degree because here you can see that O0 Wm is minus m Wm, and also O0 with with Lm is minus m Lm. So degree counting operator is only L0 and it is still there. So structure of this module is the following. Yeah, we have vacuum delta W. Here we have already on the first stage we have L minus 1 and W minus 1 acting on this vector. Then we have L minus 1 W minus 1 L minus 2 W minus 2. And then well, maybe it's already too many states, like 5 probably. No, I don't want to write them, but you can. So it looks like this.
When we act with the W1 onto W infinity, then we get a descendant in this model structure, no?
Mm-hmm.
And this should be, but in principle, it should be fixed by the model structure, no? It's the same as before. Like it's just the expectation value of that operator in within my model.
No, but now all these expectation values are independent. Before we could reduce everything to the expectation value with three primary states. But
I see. Okay. mean, but when we did the computation for L of minus k and then k, what we showed was that in that case, like when we looked at descendants, either in the incoming or in arrival states, like the difference is just something which is completely fixed by the expectation value of stuff in the primary state. Because this L of minus one was we could write them in terms of L0 stuff, basically.
Yes.
But in order to do so, we still need to know what is the expectation value of V1, let's say, on the descendants of V naught of infinity, no?
Could you say it again?
Yes.
Yeah.
So there we proved that if I understood, because probably it's not the correct thing, but we proved that basically the space is one-dimensional because it is like once we have the module structure built out of the primaries, everything can insert whatever operator we want in the middle, and we get one expression basically, always one expression.
What is one expression?
The expression for the point function, and everything else is dependent from there.
Yes, so all 3-point functions are expressed in terms of expectation value of 3 primaries.
But I mean, also the 3-point function of a descendant.
Yes, of all possible descendants.
But I mean, what we see from there is that the expectation, the 3-point function with a descendant. No, okay, because now one is positive and the other is no. So no, because now what we have shown that like the 3-point function with a descendant becomes the 3-point function with a descendant in the arrival space up to something else which is just the 3-point function of the primary. But we didn't change the degree of k. We didn't lower.
No. What do you mean? In the left-hand side, we have L minus k. In the right-hand side, we have Lk acting on a different in a different point, and also some L minus 1 which can be expressed.
Yes.
So
yes, the stuff that you underline is fine because it's just a 3-point function after numerical sufficient.
yes.
But I mean, what is left on the right hand side is still a 3-point function with a descendant.
Yes, but we can do this procedure recursively until we get primary instead of V0.
But the degree of k is not, I mean, k is the same, it's not reduced.
No, L minus k turned into Lk acting on some other module. So it's like when we move, it's like here when we move positive L's from the left hand side to the right hand side, where there are annihilation operators. So. So.
I mean, because, but then that is it 0 then?
If it is a primary state, if V infinity is primary and k is greater than 0, then of course. If so.
Okay.
Let's say if V naught is primary, then like L minus k V naught is like some descendant, and you can compute it.
Yes, but I thought that when asking for infinity, you had to change the sign of L because you had to take the joint.
Now, here, so what is written here is when we take a state, so it's we should take a joint of V infinity. Right. So we should take a joint of V infinity if we want to write it in this way. Yeah.
Right? Like the LK of infinity would be like Petrarch AK V infinity.
Mhm.
Not, it would also be like V infinity acted by L of minus K,
Mhm.
expressing the correlation function.
Yes.
Okay, okay, okay. And okay, that is fine. Now this is it's not fixed because now we are acting with now sorry this K is is positive, right? Or is negative?
So
Is a positive number.
which this? Yes.
So
Yeah.
now when we acted on a new negative, okay.
Mhm. So actually, so I did not prove this, but the general answer is that so if you insert some primary section on also on this state, the answer is so well. Let me remember. Forgot if there are two extra numbers or one. Uh, so. Hmm. Okay, so maybe that's all for today. Do you have any questions about this? And by the way, I wanted to uh, uh, also add some comment about this. So if use AGT correspondence, then all this double algebras stuff corresponds to gauge theories with groups higher than SU2. Basically, a double algebra corresponds to SUN theory. And fields which are this vertex separators which are used for Lagrangian theories correspond to degenerate Fermat modules where this descendants on the first level are all linearly dependent. In a sense, are all proportional. Uh, so and in this case, this space of conformal blocks is one-dimensional, and there are explicit formulas for them. So. So this double algebra is always generalization in the direction of higher rank of something, of gauge group, of connection. Hmm? Why is it good when the first descendants are proportional? Or well, it's a correspondence, and I don't know any a simple explanation. Why? Ah. Yes, even n equals 2 supersymmetric, so even worse. But four dimensional. Okay, so thanks for the attention.